Hello, and this is the Computer Science 434 Artificial Intelligence and Machine Learning class, Group 4. For our group project, we chose vehicle classification with convolutional neural networks. My name is Ben Moran.
I'm Alex Bailey.
I'm Kyle Grady.
And I'm Alex Stiliga.
With the rapid advancements in artificial intelligence, its applications are increasingly entering into various sectors. This includes the military sector. With the emergence of lethal autonomous weapons, or LAWs, which are autonomous military weapon systems that can independently search and engage targets with minimal human intervention, these systems have raised concerns about potential casualties during warfare. Therefore, accurately distinguishing between military and civilian vehicles has become an integral aspect of mitigating such risks. Our project seeks to address this challenge by developing an AI object detection model that can effectively classify military and civilian vehicles. We believe that our project is significant as it has practical implications in present and future conflicts, such as the ongoing situation in Ukraine. There are quite a few different deep learning models, but according to this article, convolutional neural networks, or CNNs, are the most widely used model for object detection. This is because the final layer of a CNN is able to provide a rich representation of the image. What really sets a CNN apart from other neural networks is the usage of convolutional layers. In this layer, the neurons are not connected to every neuron of the previous layer. Instead, they are only connected to specific sections. This allows the creation of feature maps and filters. These filters are able to focus in on different parts of the image for things like edge detection. The sum of these filters will allow the model to find the target object. This model has been used in many different projects, such as real-time monitoring and disaster management. This particular article goes into detail on the systems that is able to detect unmanned aerial vehicles. Due to recent conflicts causing damage to non-military targets, we feel that it is important that we have a system that is able to differentiate between military and civilian vehicles to minimize civilian casualties in future conflicts. We believe that ongoing conflict in Ukraine highlights the importance of unmanned aerial vehicles, UAVs, in modern warfare, particularly small drones. Unlike large aerial vehicles that are costly to operate and easily detected, off-the-shelf drones are small, agile, and can be used for various purposes, including surveillance, anti-personnel combat, and anti-vehicular combat. However, current drone technology lacks onboard artificial intelligence and object recognition capabilities, leaving operators to rely on raw video feeds without any useful display. By implementing a quick software system, operators could benefit from advanced object detection, making it easier to identify enemy vehicles and avoid potential civilian casualties. While this technology may not prevent catastrophic events, it could significantly reduce civilian casualties by enhancing the reconnaissance capabilities of off-the-shelf drones. Our project aims to address this gap by developing AI-assisted object recognition systems that can be integrated into UAVs for the purpose of improving their surveillance capabilities. Our long-term goal is to enable safer and more effective reconnaissance operations in conflict zones. For our LayerNet model, it works fairly well. The model has 5 layers, which mostly use the ReLU activation function, except for the final layer, which uses the softmax activation function. The optimizer we use is called Atom. The loss is represented by categorical cross entropy, and the metrics are representative of accuracy. For example, a 10 epoch model, the final results were a loss of 0.2745, an accuracy of 0.9128, a value loss of 0.2130, and a value accuracy of 0.9304.
So, our ResNet model works by using one residual block. It implements the ReLU activation function. The optimizer for this model is also Atom, and the loss is also represented by categorical cross entropy. The metrics are also represented with accuracy. With a 20 epoch model, the final results are an average accuracy of around 56%. So here you can see our 2 graphs. On the left is what we trained with 5 epochs. On the right is the training with up to 50 epochs. And you can see from the graph on the right that once you hit about the 20 epoch level is when your values start to flatten out and further training becomes a little pointless. So here are the results of our trained models. We took the models and tested them on the images from our data set. and we had it label each image with its corresponding class.
So we did quite a bit of testing on this model. Now, for this graph, all of this is LeanNet. So as you can see, there were 20 epochs per run. The image size and batch size both varied from 32 to 64. The predicted accuracy was around 50%. The ReLU activation function, we used ReLU for our activation function as well as TAN-H, and we also varied pre-processing image validation. And for most of these, we used a 6-class system. So for example, civilian aircraft, civilian car, or military truck. And then as, of course, you can also see the average predicted accuracy of around 50%. Now continuing that trend, I also went up and did up to 64 for image and batch size to see if there was any difference there. Again, not too much of a change, but recently we did run a brief test where we switched to a 2-class system, and as you can see, there was a significant increase in average predicted accuracy. For ResNet, again, compared to LeanNet, ResNet ended up being a bit better, which is what we were hoping for. If we go back and we look at the best of LeanNet, we had about 52% for average accuracy, 58.7 at the very best. Going back down to ResNet, we get up to 59.7 for predicted accuracy and 56 for average. And this is what you would expect given how ResNet works compared to LeanNet. Post-production, Ben here. I just wanted to clarify. The original dataset that we used had a 6-class system, and for the majority of our project we left it as such. It wasn't until just before the recording that we were able to run a test with a modified 2-class version of the dataset. That is why there is only one entry for a 2-class test. Furthermore, the reason why the LeanNet and ResNet results differed by so little was on account of ResNet typically being designed for models with significantly more layers than what we had at the time.
Alright, so currently, as you saw earlier, the accuracy for our models are kind of underwhelming. It's only half right most of the time. One of the main issues with that is cars and just wheeled vehicles. The system for some reason just does not like them at all, and it constantly misidentifies. As you can see, the picture of like the cartoon car says it's a military tank, and then the missile carrier for the truck, it says it's a civilian aircraft. We're unsure why, but it just keeps spitting those out. Alright, so we still have to...
The idea here is we want to test better activation functions. We also want to see if we can extend our models eventually. These are things that we would be doing if we had more time. Some of them we will hope to get more results on before our next presentation. So for example, as a long-term goal, if we had like a month or so more to work on this project, we would extend LeanNet to be a 50-layer system, especially ResNet. You would definitely see a big increase in efficiency with ResNet.
Alright, and project management. I was the GitHub expert. I handled setting all that up and making sure everyone had branches to work on and making sure everything was pushed and merged correctly. And when I was not doing this, I was either assisting with research or creating presentations, and I also created the initial ResNet program.
I was sort of the project lead for the group and had the primary responsibility of figuring out the next steps for the project and dividing up the work for the group. I got the Discord server up and running, established weekly in-person meetings, got extra time, or made sure the group had extra time to get work done, and just went around and made sure that everyone had their code running, and if anyone had any issues that they got resolved.
I was the primary researcher. If we had a problem for anything, I would find some bit of code or help to fix it, and found a lot of resources themselves. Tried doing some experimental functions of the project, such as showing the bounding boxes, but that led to be impossible. So
I was the main one that worked on the RCNN. I had some prior knowledge from past projects with regard to on how to code this sort of project. I researched and found the military vehicle dataset that we ended up using, and I also made the first major breakthrough in getting our LayNet model to work. When I wasn't coding, I spent my time researching new methods for our project, and when I found something interesting, I would share it with the rest of the group.
So, in conclusion, both ResNet and LeanNet gave subpar results for the majority of the 6 class tests that we ran. We will continue to run 2 class tests to see if we can continue to get better results with our system. So class reduction greatly improved our accuracy.
Here you can see a snippet of our LayNet code. You set up the model and specify its type, and then you add all the different layers to it. After you add your desired layers, you compile the model where you specify your optimizer, your loss function, and your metrics.
Alright, this is a bit of our ResNet code. As you can see, we have the residual block with all the stuff that makes up it, the activation functions, the normalizations. And then down at the bottom you can see how we compile it all together with the optimizer, the loss, and then the metrics for the accuracy.
And here are our references, and here's our appendix.